Role of the system operator in detecting voltage instability. An important function of the system operator is to monitor and respond to unusual power system events before the events proceed to a point at which they cannot be controlled. As a system operator, you can prevent some types of voltage instability if you can detect the conditions that may indicate pending voltage instability. In general, the response of a system operator is limited to longer-term voltage instability scenarios. Transient voltage collapse occurs too rapidly for system operator action. Classical voltage collapse that lasts for several minutes may be impacted by a system operator's response if actions are performed quickly. The following power system events may indicate pending voltage instability. 1. System voltage levels are unusually low. This may be due to heavy loads or heavy power transfer. Voltage levels should be continuously monitored. If a problem can be corrected before the voltages fall too far, voltage instability may be avoided. 2. Unusual magnitudes and directions for reactive power flows. If unusually large amounts of reactive power are flowing to one area of the system, it may point to pending voltage instability in that area. Take the example. Prior to the August 14, 2003 blackout in the Eastern interconnection, operators from several area utilities had noted unusually high VAR flow on tie lines. Unfortunately, the blackout occurred before appropriate action could be taken. 3. Heavy reactive power generation at key area generators. If key area generators are at their reactive power limit, they are not available if further reactive power is required. Avoid entering a heavy load period with low dynamic reactive power reserves. 4. ULTC adjustments fail to move the voltage. This may indicate a reactive power shortage. Responding to voltage instability. The best response to voltage instability is to prevent instability from occurring in the first place. This may not always be possible. The following methods of response are given as general guidelines. The guidelines are divided according to our three types of voltage collapse. Long-term voltage instability. Generating resources are often found in remote locations, far removed from any major load centers. Radial power systems are constructed to connect these economical generating plants to the major load centers. Hopefully, the power system designers have planned for enough dynamic reactive reserves to withstand the tremendous reactive power losses associated with heavily loaded, long radial power systems. The following precautions can be taken to prevent a long-term voltage collapse in a radial power system. A. Ensure that the power plants at the sending end of the power system have sufficient reactive power reserves to support the system and the loads. These dynamic reserves must meet the requirements of the heaviest possible load period for both normal and contingency conditions. B. All available reactive power sources at the receiving end, such as shunt capacitors, should be in service and in proper working order. Shunt reactors should be out of service. C. If series capacitors are available in the radial system, they should be in service. Series capacitors lower line reactance. When series capacitors are in service, the system's VAR losses decrease. D. If voltages are low in the transmission system, a conservative rule of thumb is to avoid the use of area ULTCs. ULTC operation can impact voltage instability in two ways. System load naturally decreases with decreasing voltage. When an ULTC operates to raise voltage, it also increases load magnitude. In addition, when ULTCs raise low side voltage, they often depress high side voltage. ULTC operation may increase the chances of a voltage collapse. E. As a last resort, a system operator should consider manually dropping load. If all possibilities to control the voltage instability are exhausted, it is better to drop load in a controlled manner than to let the system collapse in an uncontrolled manner. Systems may have automatic undervoltage relay schemes installed to trip load during low voltage periods. It is critical that these schemes are in operation during the voltage collapse-prone periods of the year. Classical voltage instability. Classical voltage instability follows a system disturbance. As a result of the disturbance, there is insufficient reactive power to satisfy the demands of the system and the customer load. The solution is simple: supply more reactive power where it is needed. The means to achieve this solution may be very difficult. To prevent classical voltage instability, a system operator, if time allows, can do the following. Maintain transfer limits within established guidelines. As MW transfer increases, reactive power losses escalate. If conditions are right for voltage instability, consider reducing system transfers to limit reactive power losses. B. Ensure that all available static reactive power sources, such as shunt capacitors, are in service. In addition, make sure that all shunt reactors are out of service. C. Ensure that sufficient dynamic reactive reserves exist to handle any probable contingency. The amount of dynamic reactive reserve is typically determined by planning and operating engineers. System operators must ensure that these minimum amounts are actually available. D. Ensure that the plant operators are providing all possible reactive power. This may mean redispatching generation. E. Generating plants in the affected area that are normally not run due to economic factors may be run to increase dynamic reactive power reserves. F. Shift system generation patterns to unload heavily loaded lines. This reduces reactive power losses since these losses are a function of the current squared. G. Consider blocking operation of the affected area's ULTCs to prevent further drops in transmission voltages. H. Request reactive power support from neighboring power systems. Neighboring systems can raise voltage at common buses. This may help raise voltages throughout the affected area. I. As a last resort, consider manually dropping load. Also be sure all automatic undervoltage load shedding schemes, if they exist, are in service. Transient voltage instability. Transient voltage instability is a rapid event from the perspective of a system operator. Once the process has begun, a system operator has little role in the final outcome. There is little a system operator can do to avoid induction motor-driven voltage instability. One suggestion is to ensure protective systems are in place and functioning properly. However, if instability of this type does occur, restoration can proceed quickly if the cause of the instability is quickly identified. Relationship of the types of voltage instability. The three types of voltage instability presented in this section are not independent of one another. For example, many of the events that occur during long-term voltage instability also occur during classical voltage instability. In addition, one type can progress into another. For instance, long-term voltage instability could turn into transient voltage instability as time progresses and events occur more rapidly. Figure relate the time frames for the three different types of voltage instability. Note that different characteristics of the system are involved with each type of instability. For example, to understand transient voltage instability, it is necessary to understand how induction motors behave. To understand long-term voltage instability, it is necessary to understand what is meant by a loss of load diversity.